Jensen, you had a slide on the number of tokens, 10x more tokens on Rubin versus Blackwell. The question I have, historically you have shown a slide of Blackwell performance versus TPUs on training. Any kind of simulation that can kind of put the performance of Rubin on the inference versus TPUs?
It's hard to, because the only thing that's available is MLPerf. And you know, we subject ourselves to a fair amount of hang on a second. I had to spit out my candy. I came without a voice. I don't know where I left it. It didn't show up today. As you know, we subject ourselves to a whole lot of benchmarking because NVIDIA is everywhere. And we're easy to benchmark, but nobody could really benchmark a TPU unless you're the TPU people, you know? And so we don't have anything to benchmark. If you guys have anything to benchmark, we're happy to take a look at it. And I think you'll find that it compares very nicely. If MLPerf is an indication, and MLPerf is quite rigorous. MLPerf is largely governed by Google, and so it's very rigorous. It's so rigorous that almost nobody finishes the test. We're the only company that has ever finished the test every time. We finish the test every time. We subject ourselves to submission every time. So you know you're allowed to take the test, and if you don't like your own answer, after you see other people's answer, you could withdraw your submission. It's the only test in the world that has this kind of civility. And we're fine with it. And so we're usually the one that submits first. And so everybody sees our answers. And then they decide whether they want to submit or not. And so my sense is that a lot of people have taken the test. Not all of them can finish it, but some of them have. I just don't think that they submit it for maybe ulterior reasons, you know. And so that tells you something. If we're the only one that submitted the test and everybody else is empty, I think that just tells you what the answer is. It's not like nobody showed up to the Olympics. They all showed up. You know, they just decided, oh, we'll just let you run by yourself. But one of the best benchmarks is actually semi-analysis. It's a living, breathing benchmark that's there. I like it because it's living and breathing. It's continuously updating, as you guys know. And so I like that fairly well. And I hope that they submit themselves to that. Because DeepSeek and Kimi, QN, these are state-of-the-art reasoning models. They're based on MOE. They're very hard. It's not for the faint of heart. You know, almost anybody can run it to completion. I mean, you'll get a token out of it. But to do it at the rates that we're talking about, it takes superhuman capabilities at that point. And this is where NVIDIA's extreme co-design capability, where we're designing across the GPU, the CPU, the NICs, the NVLink switches, the CX NICs, I mean, all of that is working together. The amount of software that has to come together for a rack that I was showing today, that pod that I was showing today, if you just think about it for a second, you know, aside from the one that you saw there today, I don't think anybody's ever seen one really, you know, built from the ground up with that kind of capability. And so NVIDIA wrote every line of code and designed every chip, created all the systems, optimized all the algorithm. We contributed everything back to open source so everybody else can take advantage of it as well. And that tells you something about, you know, the level of leadership that we have. But DeepSeek's another example. And I think today, somebody just published, is it Signal 65 or something like that? They just analyzed our performance, and it shows about a 10-to-1 from Hopper to Blackwell and 10-to-1 reduction in cost. And yet, between Hopper and Blackwell, the transistor count was only 2 times, right? And so that tells you why it's so essential anymore to do co-design at the level that we're talking about. Because if you can't change everything across the whole thing, how are you going to overcome Moore's law? If your architecture is basically the same and you're just making a faster XPU, whatever PU you like to build, if you're just building one chip, who cares? Amdahl's law gets in the way, and you're not getting that many transistors anyhow. And so I think we've fairly clearly revealed that in this new world, if you want to keep up with the rate of model size growth, 10x growth, and token growth, and cost decline, and getting to the new frontier, and you want to go fight every single one of these battles, unless you're able to keep up with the type of systems we're talking about, I think you're going to have a very hard time. I think the probabilities of keeping up with Vera Rubin is very low for the industry if you're building one chip at a time. I would say that it would, I don't want to say impossible, but it's modulo something close to impossible. It's not a one-chip wonder thing. And you're not going to build a chip, connect them in a torus point to point, because it's easier to build the interconnect if one chip connects to another chip connects to another chip. There's no switches to design. But in the case of MOE, you need all-to-all. Every single layer is an all-to-all layer. And so in our case, we literally just send information all-to-all to all the GPUs. The GPUs just send information to each other through the switch. It's one hop. In everybody else's case, you got to pass the token, from one chip to another chip to another chip, depending on the size of your pod. That could be 9 hops, it could be 5 hops. And if you're doing this repeatedly as a fundamental part of the processing, it really adds up. Amdahl's law gets in the way.